All right, today, magnets. We're talking about magnets. Yeah, that sounds right.
Yeah, there's homework.
All right.
Oh, no, there is homework.
So, to start off with, magnets have been around for a while. They weren't a thing that were created. They were kind of a thing that were discovered to start off with. Way back in the ancient times. Yeah. People found what they called lodestones. Yeah. So a lodestone, all that they were was they really had no idea. But they found it was a piece of metal that would get attracted and stick to other pieces of metal. They were pretty, I think, understandably amazed by this because they had never experienced anything that was like that at all. And usually these wound up making their way to like kings or something like that. They would buy them because they just found them interesting. They had all of the money that existed at the time. And so they would buy the lodestones and show them off to other kings to say, haha, look what I've got. And people have been pretty amazed and impressed with magnets ever since we had discovered that they existed. Now, they had no idea what was going on with them then, and we still kind of don't really know exactly what's going on with them now. But what we do know is that if you have a magnet, it will be attracted to things that react to magnets. Like iron, for example, is one of the things that is ferromagnetic is the word for things that get attracted to magnets. And so if we look at just like a standard magnet, like a bar magnet, you draw it like this. It's got two ends, a north and a south end. And there's a magnetic field that comes from it. And the magnetic field goes from the north end to the south end. So it's going to look something kind of like this.
Does anyone in here have a stats textbook?
Why are you doing stats on?
I do it home.
No, not right now, but I forgot to bring it. Want to do it.
So it looks something kind of like this.
I'm free.
Yeah, I get a better, darker marker here.
Okay.
I'm recording it, does. All right. So something like this, we've got a magnet made of north and south. So you might think, okay, well, what if we break this magnet in half? So you cut it in half, like this. Then you got a north magnet and a south magnet. Right?
No.
No, you wind up with two small magnets. They both have a north and a south end. Like this, if you break a magnet in half. But the thing is, they'll stick together. So if you break it in half and stick it back together again, it should go back together because the north end is attracted towards the south end. It's the same sort of thing like with positive and negative charges. Opposites attract in magnets as well. All right. So the thing about this is magnets line up with magnetic fields. So the north ends are attracted to the north end, or are repelled from the north ends. The south ends are attracted to the north ends, and looking at it that way. But the other thing is that magnets are, they align themselves with the local magnetic field. So we put like a small compass needle, something like this here, in this magnetic field. Well, right now it's not aligned with the magnetic field because what direction is the magnetic field going? Right here?
Down.
Down. And so this is going to rotate if it's free to rotate. And it'll rotate so it aligns with the magnetic field.
That's how a compass works.
Yeah, that's the way that a compass works. There we go.
They don't go
And so
north.
it would line up this way, with this being the north end of the compass. Make sense so far? All right, what direction's north?
Up.
No, right here. Like, what direction's north?
Oh.
Never saw you walk that.
Well, that's the east end.
Yeah, this is the west end.
Oh, this is the west
So
east.
never east.
That way.
I still think it's up.
This way's north.
Oh.
No.
Because
Right.
this is west, this is the west end of the building, that's the east end of the building, so north is that way.
Yeah,
Okay.
absolutely right.
Yeah, think about 47. 47 goes that way.
We'll be on a run in our
47 runs north and south.
Yeah, fair. It's good to know that. You don't get lost as much if you always know the direction that north is. Or at least any direction. Doesn't matter if it's north. If you always remember west, that's fine too.
I go with the sun.
I remember finding it.
I don't usually know where the sun is at all times.
Oh, I do.
Oh, where's it? Can you point towards
Right
it?
now, it is that one.
Yeah, it's to the south.
Wow.
That doesn't mean it's in the
That
west.
way.
So
It's probably like a band.
Okay, let's.
Anyway, that's not important. The next question is, did you know that the Earth is a magnet?
Yeah, yes, I did.
Yeah, the Earth is a magnet. It's a big old magnet. It's the biggest magnet we've got,
And they messed it up.
nearby at least. It's not the strongest magnet that we have, though. It's just the biggest magnet. And so there's a magnetic field that goes all the way around the Earth. And so the Earth has a magnetic north and south pole as well. I like to point towards the magnetic north pole now. It actually is generally this direction.
Oh,
And the reason why is, here's what happens. You take a compass, the north end of your compass points towards in the north direction, which is the south pole of the magnet that is the Earth. So at the top of the Earth, the North Pole, nearby to the North Pole is the magnetic south pole of the Earth. It's kind of interesting.
Why is it called?
Because that's the direction that the compass, the north on the compass points towards the North Pole. It'd be a little more confusing if the north part of your compass points south. So instead they do it this way. The actual magnet of the Earth is the other way around.
Are there west and east poles on the magnet?
No.
That we discussed.
Right. So we don't have just you can't just have a north magnet or just a south magnet. They always come in pairs like this. There's a direction. And so what you'll notice is that the magnetic fields, actually, what they do is they kind of loop around, and then they'll continue on through the magnet from the south to north on the inside, and then come back around. And so you get these closed loops. And that's one of the things that we get with magnetic fields is that they're always closed loops in this case. Now, between magnets and magnets, really the thing you have to keep in mind is that north is attracted towards south, or in the case that north will line up along the direction of the field. But that's most of what we're going to do with and the other thing I guess is that you know that the field lines point out of the north end and into the south end. And if you know that stuff, that's about as detailed as we go into permanent magnets. Permanent magnets are immensely complicated. If you are studying physics in college, you won't get into them during your undergraduate degree because there's not really much you can talk about with them at that point. Yeah.
Is the north side as strong as the south side?
Yep. They're basically equivalent. Yeah. There was we did, you know, when I worked at the company that was making speakers, microphones, those have magnets inside of them. There was one guy who was like the magnets guy, and he had a big beard, long hair, and you'd go up to him and you ask him a thing about magnets, and he would just say, "That's not going to work. I can't really explain to you why." And then he would say, and people would just say, "Great," and then walk away and they'd try something else.
He'd be like, no.
Yeah, he was like the magnet wizard at the company. And
I want to be a man.
well, you got a few graduate degrees to get, and then you can be the magnets
That
expert
was the
somewhere.
check anyway, so it's fine.
Yeah, there we go. All right. So what we're going to do now is talk about what happens when we have electric charges in magnetic fields. Now, what we're going to start off with before we even get there is we've got to come up with a symbol for magnetic field. So pick like a reasonable symbol. Yeah, that's what I was thinking too. I was thinking a capital letter B would be a good one to use in this case. So we use that.
Yeah.
Capital letter B, this is the symbol for magnetic field. Now it comes after A and before E, so seems like a good choice. The actual story of this one, I believe, is that the person that was coming up with the theory of electromagnetism was just he came up with a whole bunch of different fields, and he had like A through G. And the reason why E for electric field is E, it's not because it's the electric field, it's just because it was the fifth one in his list of fields. So D was for magnetic field, and E was for electric field.
Wait, it was for what?
What's A for?
Well, what's like
D is a different kind of electric field.
What's A for?
I don't remember. There's only 4 of them that we still actually use. Which is, it went all the way to H, because H is the other one that we use for a different version of the magnetic field, and then there's I think it's the D field, which is the other version of the electric field, but we're not going to get into those in this class. All right. Yeah, those other ones are basically like, the electric field inside of a dielectric uses the other kind of electric field. But again, we're not really going to get into that. All right, so we've got that here, and there are some things that people notice about magnetic fields. Is if you have moving charges in a magnetic field, they feel a force. And over the years, things were, the investigations were taken to figure out, hey, what's the relationship between these? Some of the first things that were discovered was that the magnetic force, which we'll write as F sub B, is proportional to the strength of the magnetic field, which seems reasonable. The magnetic force on a charged particle is proportional to the strength of the field. So if the field goes up, then the force goes up. Another thing that maybe wasn't as obvious, but was also noticed, was that the magnetic force is proportional to the velocity of the charged particle. If the charged particle is moving faster, it feels a larger magnetic force. Yeah, it's kind of interesting when you think about it and look at it that way. Another thing that we have is something about the direction, the nature of the direction of this, that was later noticed as well, which is that if the velocity is parallel to the magnetic field, then the force is zero. There's no force. The magnetic field and the velocity are in the same direction, then we get no force for magnets. What was that?
Like fluxes.
Kind of. More specifically, this reminds me of something when two vectors are parallel, and we get a result of 0.
Parallel.
Yeah. We've got dot products and
The dot product equals 0.
cross products. Because a dot product, when two things are parallel, you wind up with a value, and when they're perpendicular, you get 0. But with a cross product, it's the other way around. When they're parallel, you get 0, and when they're perpendicular, you get not 0. And so this recommendation here, when we get into it, this sort of suggests a specific relationship. And when you look at it then, you get to this idea that the force, magnetic force, is proportional to the sine of the angle between the two, sine theta. And so what we get is an equation for the magnetic force, which is QV cross B.
Forgot how to do cross products, I'll be honest.
We'll go through them here in a bit. All right. And so what we're going to do right now is look at this equation, think about it a little bit. Or I guess you could also write this as that the magnitude of this is going to be equal to just QVB sine theta. Does that make sense? Because remember, that's what cross product is. It's just the two things multiplied together times the sine theta. Because if they're in the same direction, it's 0. If they're perpendicular, it's just equal to all those products multiplied together. If it's somewhere in between, you get a fraction of the total maximum theoretical value. That makes sense. So if you want the biggest field, the biggest force from a magnetic field, you want to make sure that it's moving perpendicularly to the magnetic field. Does that make sense? Yes, and quickly. And has a large charge. And the magnetic field is strong. All of these things. Does this make a bit of sense? I guess I could have also mentioned it's also proportional to the strength of the charge. I didn't put that in there as well. Oh, and I guess one other thing that was noticed that was recognized about this was that the force is always perpendicular to the velocity, and it's also always perpendicular to the field.
One more time, do happen.
All right. So these are some of the things that were noticed about magnetic forces and magnetic fields for charged particles moving in magnetic fields. And if you recall, last time we used cross products was, I think, back with torque and angular momentum. And there was something that we did with those. There's a specific device that you'll need with you to make these calculations.
No, it was rolling.
You have it with you all the time.
No, not right hand.
It's connected to the end of your arm. Yes, that's right. It's your right hand. Trusty right hand, always there to help you when you need to figure out. I haven't yet.
What happened?
I would teach them how to do left-hand rule, or you have to visualize a hand in your head. Those are the two methods. No, I mean once you get good enough at this, you can just do it mentally. I wouldn't suggest doing it that way because you'll probably get questions wrong if you do it that way. So here's what we're gonna do. We're gonna do some practice on. Well, actually, even before we do that, I guess before we do the right-hand rule, there's a couple things I wanted to mention, which was basically the difference between electric forces and magnetic forces. So before we had electric forces, the force is just equal to Q times E, right? That's the electric force, it's just Q times E, the charge times the electric field. And so here's a few of the differences. The first difference would be that while electric field and electric force are parallel, magnetic field is perpendicular to the magnetic force. That's one of our first changes, one of the first things that's different about it. The second one that's different is if velocity is 0, you know, the electric force is still exactly the same. It's not affected. It's just QE. But the magnetic force is 0. So that's the thing that's different. If there's no moving charges, there's no forces between those things. And the third one is, this one is something that sort of follows a little bit from this, is that the magnetic field, we said, is always, or the magnetic force is always perpendicular to the velocity as well. So what happens if you apply a force to an object perpendicular to the direction it's moving? It turns. And one thing that it doesn't do is slow down or speed up. It doesn't change its speed. So what that means is that magnetic forces cannot directly do work. Now there are some ways that they can indirectly do work, but we're gonna right now, while we're dealing with individual single particles, they can't do any work because the force is always perpendicular to the direction of motion. If it starts moving a different direction, the force also is pointing in a different direction now. All right, time for some practice. We'll do some right-hand rule practice.
I love right-hand rule practice.
Good. So limber up. Get your right hands ready. We don't want any right-hand rule injuries in here. All right. So the first example we have is going to be, we've got magnetic field going up. We've got a positive charge with the velocity to the right. Magnetic field going up, velocity going to the right. Now, right-hand rule. You start off, and I guess I'll write this back up here one more time. Magnetic force is equal to Q V cross V. And so the way that this works is you
You'll have to do this every time.
Yeah, definitely. So what you do is you take your fingers, point them in the direction of the first term, the velocity. So which way is it going? This way, right? Then you rotate your hand until you can curl your fingers in the direction of the magnetic field, which is this way. And which way is your thumb pointing? Towards you. And so that's the direction of the force. The force is towards you. See, it's easy. All right?
Oh, I was doing a left hand.
Yeah, don't do that. You'll get the wrong answers if you use your left hand.
Well, you just have to make it negative.
Yeah, fine. Multiply your hand by -1, and then you'll be right. Okay.
What if they're a double amputee, though? Like, no hands?
Then I said you visualize it.
Imagine you had hands.
So there is a way to do this mathematically with matrices and vectors if you want to do cross products that way, but we're not going to do that in here. All right, so that's our first example. Now, here's the thing. You'll notice that in this case, I've drawn arrows that are up and to the right. It's easy to draw arrows that are down and to the left. It's a little harder to draw arrows this way, towards you, or this way. So I'll show you how to draw an arrow that goes in or out of a piece of paper or a board.
It's like an axe, isn't it? Oh.
These are the drawings. This one means it's going into the board. This one means it's coming out of the board. It's easy to remember if you think about an arrow, like a bow and arrow.
X is out.
Give me a second. Think about a bow and arrow. If a bow and arrow is coming towards you, you see the point of the arrow. If a bow and arrow is going away from you, if an arrow is going away from you, you see the feathers, the tails on the back. Yeah, the fletching. And so that's why here you see the back of the arrow. Here you see the tip of the arrow coming towards you. This is coming out. This is going in. That makes sense? This is how you draw an arrow that points outwards. If you're trying to draw an arrow that comes outwards and at an angle, don't do that. Yeah, pick a different perspective to draw your picture in, so you don't have to do that. So, also sometimes you won't see the circle around it, you'll just see the dots or the crosses. And that's often if you're doing like a magnetic field, like we'll see in this example here. Do it like this. We've got a magnetic field shown here. And direction did I say? Yeah, we've got a positive charge moving downwards. What direction is the force? You point your fingers in the direction of the velocity to start with, and then you rotate your hand until you can curl your fingers in the direction of the magnetic field.
Yeah.
See, I've deliberately chosen some easy ones for you. Then for me, they're pretty easy because I just do it like this, because I'm facing this way, and so you can see downwards like this. The force that way. So that is one thing. Rotating your body makes some of these easy.
Wait, how do you do that?
Yeah, RightHand Rule actually works.
Don't you have to like sideways?
Yeah, just turn around.
So if they're going-
So it's like
Do a 180 turn.
this.
Be looking this way.
Now, real quick, is this into or out of the board? The magnetic field?
Into.
Into the board. The magnetic field's pointing this way.
So you're going
See,
to grab the magnetic field.
point your fingers downwards, and then you curl your fingers so that they're in the direction of the field, which is that way. So your fingers are pointing that way. So you rotate your hand so that your palm is facing towards the direction of the magnetic field.
Oh wait, that's because my thumb was like this.
Yeah, and then your thumb points this way. So the magnetic force is going to be in this direction in this example. That make sense? Yes, no, maybe?
Yes.
Okay, we'll see another one. We've got like 8 of these, so we'll kind of keep going through them.
I stole Sean's backpack today and he said no.
Yeah, I don't see you.
All right, next up we have magnetic field going this way, and velocity in that direction.
Does it matter if it's, I don't know.
Mhm.
It does matter?
Yep.
Of course it does.
So point your fingers in the direction of the velocity, the way it's going, and you rotate your hand until your palm is sort of pointing towards the direction of the field, which is this way. And then you curl your fingers so that they're pointing in that direction. Like this.
Oh.
Into the board. Yep. So we got velocity this way. Like this. Does that make sense? All right, let's try another one. We've got here. Right. So the velocity is this way, and the force is upwards.
Okay.
Which way is the field?
So velocity is this.
Towards away from the board.
No, curl.
And for your curl.
So first thing that we need to start with is that the magnetic field is going to be perpendicular to the force. We know that that's got to be true because the force and the magnetic field have to be perpendicular. So what we do in this case, we point our fingers in the direction of the velocity, and we know that the result is our thumb has to be directed in the direction of the force.
Yeah.
So the force is your thumb in this case. So this way, and so your fingers would have to curl in this direction. So what does that mean about the magnetic field?
It's away from the
We say it's this way?
towards us.
That's mostly correct.
Mostly?
Yep. Because what did we say about
Turn.
the component that was parallel to the direction of motion? That doesn't affect it, doesn't cause any force to it. So it could be here, it could also be this direction. could be this direction. It could be really anywhere in this half plane, like this. Because notice, if it was this way, you'd still get the exact same thing, right? You point your hands this way, curl like that, you'd still get upwards force. If the force was this way, you do the same thing. You point your hands like this, you curl them until they went back that way, you'd get an upwards force. And so it could be anywhere in this half plane, in that direction. Does that make sense? Yes, no, maybe? Okay. So, yeah, if you're going backwards to find the force of the velocity, it doesn't necessarily give you exactly but it doesn't tell you 100% what it is. But it does, you do know that there has to be a component this way, and there may or may not be a component in this direction. We know that there's no component in this direction because of the way that the force is pointing. Does that make sense?
Yep.
All right, let's try a couple more.
No. Say that. She said she had results.
And then she was absent today.
No, she said she was meeting with the surgeon.
This is our magnetic field.
She sent out a
Email like this morning.
Yeah, last night. But at this
Boom.
appointment, I'm gonna take it.
Hold on, bro.
What?
Wait.
Four.
Why am I so dumb? This isn't
Once you figured out the direction, you don't have to keep holding your hand where it is. You can just point with your finger or something like that. Once you
I like this better though.
Yeah, that's true. So yeah, we do downwards, like this, and then from there, the magnetic field is pointing this way, so I need to curl my fingers this direction. We wind up with that.
Oh, I had it right.
Into the board. So you point your hands in the direction of velocity to start with, and the magnetic field is this way. My palm is already facing in that direction, generally. You don't turn, because you need to continue to point your fingers in the direction of the velocity to start with, and then you curl your hands this way. All right. We'll do just a few more of this. This time we're going to have a different magnetic field. It's going to be like this. So first thing is to identify the direction of the magnetic field.
What's the dots and boxes? But it's an electron. What does it mean when it's an electron?
We'll take a guess.
Opposite direction. Oh, no, when it's an electron, you do a left-hand rule.
Actually, might make sense.
Is he right?
We'll see.
Hold on.
I think it is. That's on.
So you point your fingers in the direction of the velocity, right? Then you curl your fingers in the direction of the field. And so it feels an upwards force, because it's an electron, or it's a negative charge.
Oh, so I was right? It's a left-hand rule?
Yeah, multiply your hand by -1. Or you could use your left hand. That is a thing that some people suggest.
Left-hand is
That's what I do.
You can do it that way if you want to, but in general, I would suggest just still using your right hand and then thinking it's in the opposite direction. Because then you can answer questions arbitrarily to say like the direction that the field would be, and it's just that you're multiplying by a negative charge to the force flips.
Yeah.
That's an equation.
I do positive charges with my
So you can do it whichever way you want to.
and I do negative with my right hand. This guy. You're always doing it. I like to use it myself.
This is one of the again with the right-hand rule, one of the rare occasions when left-handed people are slightly at an advantage because your right hand is already free to do all of the manipulations. You don't have to put a pen down or anything to use your right-hand rule. All right, got a couple more here.
It's like.
Oh, Charlie. I get 185 on the income. So left-hand.
And since we see both of these vectors are in the plane of the board, it means that it has to either be out of or into the board when you look at these ones. So you can start off with this, velocity this way, rotate,
It's going
fingers
out.
this direction, my thumb points into the board, so the force is out of the board. It's a negative charge.
So? I'm not going to believe any of this until we do a lab and prove it. This is all fake.
Yeah, this is one thing about this as well. This topic that we're about to come up to, like within electromagnetism, this is truly the first thing that's actually three-dimensional that we've done all year. Because everything before then, you could flatten in 2 dimensions and it would still be exactly the same, even if we did the problem in multiple dimensions. But this is the first thing that actually winds up being truly three-dimensional as we look at it. All right, so we've got this here, and then we'll say we've got a negative charge.
Should I keep this unit? Will it?
Magnetic field.
Then we get it. This unit.
That's the velocity.
Oh, because it's three-dimensional.
Wait, but they're parallel.
Zero.
Yeah, it's 0, right?
It's negative 0. I think it's negative 0.
It's 0.
So we previously said if the two are parallel, then the force is 0. And it is. Because the angle between the magnetic field and the velocity here is 180, right? 180 degrees. Sine of 180 is 0. The other way you can do it too is if you point your fingers in the direction of the velocity, and then you curl them in the direction of the magnetic field, well, no matter which way you go, you're still getting point towards it. So there's no direction that you could, no way you could argue to be in any particular direction. So it has to be multiplied by 0, and then it can be in any direction you want. What was that? Who came up with it? I mean, it sort of came out of vector calculus. So that's part of it.
Vector calculus.
Yeah, vector calculus, that's Calc 3.
Oh, man.
So we're just doing a little bit of Calc 3.
Why is
Are we
there
actually?
3 calculus?
Yeah, calculator is just multivariable.
Oh, you think there's only 3 calculuses?
Why is there more than 3 calculus?
No, there's really
Not
only
that
like
much
3. There's really only 3 calculus.
There's only 3 I have 6 in my major. It's like Calc 1, 2,
Yeah.
Calc 1, 2, 3, and then there's like linear algebra.
All right. So this is the what sometimes is called magnetostatics is what we're looking at here. We already did electrostatics, but this is magnetostatics because the magnetic fields don't change,
I love Magneto.
but the electric charges are moving. So it's not electrostatic, but it is magnetostatic. So you get these sorts of forces on charged particles as they move around. This is what we're going to be analyzing is mainly electric charges moving in a magnetic field because that's something that we can do. We have the math for it, and we'll continue to see it. So let's take a quick look at an example one more time of, let's say we've got a positive, or sorry, a magnetic field that's coming out of the board, something like this.
It's like, we got one in here.
So we've got a charge moving this direction. Which way is it going to feel the force?
It's a
Is
positive
it
or
force or the-
Well, then tell me either way. This is the field.
It'll feel it along the z axis.
Well, answer the question either way.
It's down or up?
Yeah, which one's which though?
Down if it's negative.
down if it's positive.
No, down if it's negative.
No,
down.
dot is out.
This is magnetic field out of the board.
Shoot. Yeah, that's what I meant. I did with my left hand. I'm sorry. I messed it up.
Oh,
All right, so let's say it's positive then. It's got a downward force. So what's that going to do to this object if it has a downward force?
Turn it to the right.
Turning.
It's going to turn to its right. That make sense? Okay. Later on, it's going to be going then something like this. What's it going to do now?
nothing.
What direction is the field going to be now?
It's fine where
No,
it is.
turn to its right again.
It won't move at all.
The force.
It's gonna
Go
go
that way.
Okay. So now we've got velocity this way. Curl this direction. We wind up with the force this way. Then it's going to be going this direction. And it's going to continue to turn right. So what kind of motion is this?
rolling.
Emotion.
Circular motion. So there's a reason I taught you that poem or rap or rhyme or whatever about circular motion.
Circular motion requires a force towards the
Centripetal towards the center. Yeah.
F equals
Tie
MA.
a really light string to this. Can we calculate the force?
F
That'd be
equals.
like-
I don't know.
How in physics are like, oh, they attach a really light string.
We'll have to see what the actual values of the forces are for reasonable charges, and we'll see what we get.
I'm on board for this.
Okay.
However, is there any rolling involved in this unit?
Not really.
Not really.
This is just circular motion.
Yes, I'm saying, but is there any rolling?
I mean, we could probably.
I don't know how to do rolling. I don't know how to do rolling.
Not really in this unit. The next unit, there's at least one problem on the homework that does have some rolling, but that's not this unit. All right.
I don't know.
Are we okay with this so far? Let's go ahead and do a calculation for this. Let's say that this is a proton. All right, since we got a positive charge there. So, anybody remember the charge of a proton?
1.6 times 10 to the negative 7 coulombs. No, 19. That's what I meant.
I was right.
Okay, so that's the charge of a proton. Does anybody remember the mass of a proton? It's
Negative
negative
9.11 times 10 to the negative
27.
27.
Negative 27.
That's kind of halfway between the mass of a. That's half. You're using the number from mass of the electron. Oh, so that's not quite it. Well, we'll get there in just a second. What I actually want you to figure out first for me, though, is well, we already know Q. Let's say that this proton is traveling at a reasonable velocity of. But I'm not quite that close to light speed. We'll say like 3% of light speed. So it's going like 10,000 meters per second.
Do that.
That's my mile speed.
Well, you got some records there. The only issue is if you're charged and going that fast, you feel all sorts of weird forces.
Well done.
So that is the speed it's going. And let's say that it's in a magnetic field of, I guess I didn't tell you what the unit for a magnetic field is. So the unit for magnetic field is measured in Teslas.
Teslas?
Yep.
I used a Tesla on my deck. It got nerfed recently, and its speed decreased, which made it attack.
Okay.
What is he saying?
So the unit, the way that this is written, it's a capital letter T.
Is he actually?
Okay.
Is that how new magnets are?
Not like Tesla the car, like Tesla
Bro,
the
what
guy.
did you
Yeah,
do?
Nikola Tesla.
Yeah.
That was not that long ago.
Yeah, so like that's the unit's named after him. Yeah.
Oh my god. That was me for Waxesium.
So when we look at this, let's say that the magnetic field of this is going to be, and it kind of follows the trend of most stuff in electromagnetism where the units are too big to really be practical. So we'll say that this is a magnetic field of, we'll say 7 millitesla. Okay.
Is Tesla anything that we need? Is it like how whatever it was like volts per meter? Is it any does it break up into anything?
Yeah, but we don't really use them.
Thank God.
I mean, I guess you could call it like newtons per coulomb meter per second. Because then if you look back at the equation that we had, F is equal to QV cross V, V just needs to be whatever units that you need to cancel out to get newtons on the other side of the equation. So let's figure out what the force is. Tell me what the force is. Probably need a calculator for this.
No.
Yeah.
It's just one person.
Yeah.
Q times V.
It's already shot back.
The force.
Is that
Your starter is
Natural person is not negative 3.
7 and
Millitesla. Milli. 1/1000. Mil stands for 1,000.
So it's -3.
Like a millimeter. Yeah, so 0.007.
9, 8,
What's theta?
90. 70 plus 42. I got it.
So, we get a force?
I had -7 as well. We got -7.
1 point what?
I had negative 8
Hey,
problems.
would you? No, bad. Okay, I messed up so bad.
To what?
Negative 17.
Wait, I didn't get the. Wait, did you multiply by sign?
On a 9, are you in
It's
regular?
signed. His ID is gone.
Yeah, no, I was saying. I did what I did. I would do it. I hate calculus. Why do they teach
Wait a second. How does that matter? A? A?
Why don't we just?
Are we good with that number?
Why don't we just do it?
Yeah.
Yeah.
Okay. So, this is this number there. That's the force. What we want to figure out next is what's the acceleration of this thing.
force equals mass times acceleration?
Yeah, and the mass of a proton is 1.67 times 10 to the minus 27.
Oh, I call it. It's electron negative 31.
Yeah, it's
Kilograms or
9.11 times 10 to the minus
Wait.
kilograms.
Oh.
So what's the acceleration?
One point
Just F equals ma.
1.8 E
Like a lot. I don't know why.
It's this over that.
44.
This divided by that.
Oh, you divide them?
Yeah.
F equals MA.
F equals ma.
Well, we can think about this number so
A equals F over M.
than that one.
I got 6.7
Oh, someone
million.
wrote a bad word right now.
Yeah.
Look at the bad word.
Oh,
Times 10 to the what?
million? I don't know.
One more than a million.
6.
5, 6, 7, 8, 9, 9
Oh, billion.
billion.
Yeah, billion.
There we go. So that's our acceleration, 6.7
It's like the acceleration you just
Billion.
billion meters per second squared.
That's Alex Johnson's acceleration.
Well, the thing is, though, this is perpendicular to the direction of motion. It doesn't speed up or slow down the object. All it does is turn it. But it's going pretty fast, so in order for it to be going in a reasonable sized circle, it needs to have a quite large acceleration. Remember, it's v squared over r. So let's figure out a little bit about the size circle that this is going in. Okay, so circular motion requires force centripetal towards the center. F equals ma, but a is
Different.
it's
V R over T.
V squared over T.
4 pi R squared.
it's v squared over r. That's right.
So I thought. Oh my god.
4 pi squared
You go like this, 4
R over T.
So the magnetic force is going to be equal to the centripetal force. That's the thing that's causing it to go in a circle. And so we got here, on this side, it's going to be QVB. Sine theta, but sine theta, we're just going to assume is equal to 1. Okay? So QVB, that's the magnetic force here. That's going to be equal to M v squared over r.
I took 100 day pull. That's why I've been taking day pull all day.
Does that make sense? Circular motion equation. The force is being supplied by magnetic force. That's the centripetal force. So we can use it here to solve for whatever we wanted to. So what I'd like you to figure out is, what's the radius?
Oh, I think it's
Just solve the equation here. Just the equation
Oh.
analytically with the variables. Solve for r. That's just a little bit of basic algebra. We got it.
Times
So
R divide all that other stuff over.
Yeah, yeah.
It's MV Q over QB. Are the V's different?
no.
No, they're not. But I'm just showing you that. So see, all we have to do is just swap position of this r and this QVB, and we get this right here.
What's the velocity?
So I'd like for you to figure out for me, what's the radius of the circle that this proton is circling in?
It's supposed to be as big as
What?
0, 1,
It's smaller.
This is a strange thing to say.
Why did you admit that out loud?
He's not even here.
I'm making
Yeah, kids not even here.
big foot for being fat.
What?
Can't quite see the numbers.
Oh, sorry. 1.5 times 10 to the minus 6 meters. Yep. So that is 1.5 micrometers, or microns. That's the size of the circle. It's pretty small. It's a millionth of a meter.
Oh wait. Never mind.
Yeah, but for the size of a proton,
Oh, holy
a proton the size of a the size of an atom.
Small.
The size of an atom is about 10 to the minus 10 meters. And so this would be like, what, 1,000, 10,000 atoms? Circle about the size of 10,000 atoms.
Yeah, that's like a mile.
Not a mile.
It's not like a super short distance for an atom, but it's not a huge circle either.
This was as skinny as Tyler's waist, right?
All right.
He's so skinny. He's
So we've got some relationships that we were able to derive here, especially for the circular motion of a charged particle. We'll get a little more into depth on that in here tomorrow and look at some examples and some applications of why and how we might be able to use this kind of force. There's a web assign that goes through mostly right-hand rule stuff. Most of those have 1 or 2 tries, so think about it as you go. And then,
I forgot what
is that it?
RightHand Rule was.
I feel like that's it.
I can't start again.
Oh, there's also some that are doing some calculations for QVB, sine theta, some of those sorts of calculations. That's what we got today.